Okay, so chapter 10 is about energy, and energy is the ability to do work or produce heat. Now, most of the time when we talk about potential energy in chemistry, we're going to be talking about the composition of chemical bonds. And an example of something that has a lot of potential energy in its bonds are fossil fuels. So like gasoline, which is a lot of octane, propane, methane. Those are all things, these hydrocarbons, these fossil fuels, that have a lot of potential energy in their chemical bonds. This is more of a physics look at it. Now, we also talk about kinetic energy, the energy due to motion as these molecules are moving around. The faster they go, the more energy they've got. So we'll talk about those two in the next slides here. So, some definitions that you should be familiar with: conservation of energy, that we can't convert from one form. We can convert from one form to another, but we can't create or destroy it. So unless you're doing like nuclear work, E equals mc squared, it's not going to be converted from mass to energy. But we could take something that has a lot of potential energy, like fossil fuels, and convert it to heat, do some work, and then the rest of it gets converted to heat. That happens a lot. Because all energy cannot be used for work, you're always going to lose some to friction. And even if you don't, it's still not converted to all work, but that's a different story. But we have a lot of friction, and what happens is things heat up. So temperature is a measure of the random motion of the molecules. So when I talk about temperature, I'm just talking about, on average, how fast are these molecules moving. Heat, though, on the other hand, is a flow of energy due to a temperature difference. So we'll talk about heat flow as Q, or sometimes we talk about it as enthalpy, which is delta H. So as you'll see in the next slides, that's how we're going to talk about that. Just talking about cold water and hot water coming to thermal equilibrium. If we had some molecules moving super fast, and those little lines indicate they're moving fast, and they come into contact with molecules moving really slowly, what's going to happen is all 6 of them eventually, they're not going to line up like this, but all 6 of them will have about an average of the 2. And again, when I talk about an average of the 2, it's the average of between this speed and this speed. But also, I want to have you understand, and this is kind of a weird concept to think about, but this is just an average kinetic energy. They're not all moving this fast. Some are moving faster, some are moving slower, but on average, they're moving at an average between the fast and the slow. All right, so we talk about exothermic and endothermic processes, and those are important to understand. What's key to this is understanding what the system is, and usually we have to focus in on the molecules for the system. And the surroundings are everything else in the universe, which sounds kind of drastic, but for instance, we're talking about a beaker of a substance, and we have some molecules in it. The molecules themselves, these little black dots, are the system, and the water and the beaker and then everything else beyond that is the surroundings. So think about that and try to visualize that. Endothermic energy goes into the system, so energy from the water and the beaker go into these little black dots. So first aid pack, chemicals take in that energy and leave the pack in your skin cold. In an exothermic system, the energy goes out of the system. These little molecules give up their stored energy, and we feel the warmth. Now, feeling warmth or feeling cold is not always the way to define it. We're going to look at some systems that give up energy and change state. But if you think about just like an ice pack or gasoline burning, you would feel the change in temperature there because the heat flow is into the system or into the molecules for endothermic and out of the molecules for exothermic. But let's take a look at some other systems too. So for an endothermic graph, and it's important that you understand that, if we do an energy versus time as it goes on, in an endothermic graph, the reactants start out pretty low energy, and the products, so the reactants, are down here, and the products are up here. And the reason that the products have more energy over time is because from the surroundings, the heat's being taken. So the water is cold, your hands are cold, and these little molecules are taking in this energy, and the resulting product has more energy. Now that's not as common. What's more common is in an energy versus time graph is having these chemicals have quite a lot of potential energy. And so the reactants here have quite a lot of potential energy. A great example, again, is like gasoline. And what happens is we ignite it, a little spark called activation energy. And what happens is then the surroundings gets all kinds of energy. So you feel that heat. And the products of combustion, when gasoline combusts with oxygen, the products being CO2 and water don't have hardly any energy at all. Now they have their own uses and their own problems, which we'll talk about in the climate change video, but the products don't have energy nearly as much as the reactants did. Okay, so this is another example of exo or endothermic where it can get a little tricky. If I'm going from a solid to a liquid to a gas, so let's say I'm going from ice to liquid to steam over here, what has to happen is heat has to go into those molecules. Heat has to go in, and because of that, it's endothermic. And this can get kind of tricky because people look at that and go, oh, steam, it's hot. Yeah, it's hot, but the reason it's hot is because we had to do something. We had to put heat into the system. It's not like the system's giving up energy. We had to put heat into the system for the system to do this. So just kind of be careful about that. And then gas to liquid to solid, if we have a steam engine, that steam engine can do work, but also it does that by condensing. And when it condenses, it releases energy. If you've ever had a steam burn or some kind of burn, you know that energy has been released onto your skin. So that is exothermic. So careful with those phase changes. They can be a little confusing. All right, so the second part here is called specific heat capacity. And I'm not going to spend a ton of time talking about this. You can read through it. But this is the way things heat up and cool down. And this translational energy, this is how to best, I should say. They all increase temperature, but this is the best way to increase temperature. So what happens is water tends to do the first three things to increase temperature, and iron atoms, for instance, do the fourth. So what happens is that water can absorb more heat than iron for the same temperature change. And this is called specific heat capacity. So you could think of specific heat capacity as thermal inertia, a resistance to change. Now, this conversion right here is something that you need to know. But the listing of all heat capacities are on page 350, and they all are given to you. The larger the number, this is the bigger thing, the larger the specific heat capacity, the lower the temp change. Okay, so you're going to go ahead and put a ton of energy into the system, and the system is really not going to be that impressed. It's going to nudge up a little, maybe down a little. But the higher the number is, the more resistant it is to change. Okay, so here's some examples because the changes are very slow here. The water is actually very, very cold in the spring. The temperature, air temperature is wonderful, but the water is not, so you have to be really careful with that. All right, so as far as the formula goes, Q is equal to S times M times delta T. This is in joules. This is our heat capacity in joules per gram degree Celsius, our mass in grams, and our change in temperature, so from the beginning to the end, degrees Celsius. Also, if you ever need to convert, you can use that conversion chart. All right, so quickly what I'm going to do is just asks me how much energy, so I'm just going to use this formula. And it asks me how much energy is required, so it's going to go into the system. It's endothermic. I need to look up the specific heat capacity of iron, and it happens to be 0.45. Has nothing to do with this 45, just happens to be that. Look that up in the table, and so I'm going to go 0.45 joules per gram degree Celsius times the mass, which happens to be 45 grams. times the change in temperature, and that's going to be 78 minus 22. So when you're doing that, make sure that you are doing the change in temperature, so 56 degrees Celsius. So that cancels. So times 45 times 0.45, we're going to get 1134 joules, and that's energy going into the system. Okay. A piece of aluminum is cooled, so energy is going to get released. So this is exothermic. Q is equal to S times M times delta T. Aluminum's heat capacity, again, you can look that up on a table. Joules per gram degrees Celsius. We're looking for the mass, and the change of temperature is 400 degrees Celsius from 600 down to 200. So to find the mass, we're just going to have to go 4,000 divided by 0.89 times 400. And definitely make sure that you put brackets around that, otherwise it does not work. Okay, so the mass must be 11.2 grams. All right, now this is gets a little bit trickier in the sense that we are going to drop one thing into another thing. And the metal's going to cool down, and the water is going to heat up. And so, I'm trying to go too fast here. My recording time is almost up. That's an M. All right, so I'm just going to keep this separate. We don't know what the heat capacity of the metal is. We know it's 15.6 grams. And here's the other thing. It's going to come to an equilibrium temperature of 27, and it started at 100. So we want to go 100 minus 27. And I just realized here that I'm not going to make my recording time, so I'll just make another recording after this. The water heat capacity is 4.184. You can look that up on the table. The mass of the water is 100 grams, and this is really like your lab. It's exactly like your lab. And it came to 27 degrees, but it started at 25. Now, notice I am doing this, so I'm only going to get positive numbers here, so make sure it's the hotter minus that. All right, so what I'm going to do is kind of clean this up a little bit. 15.6 times 73, 4.184 times 100 times 2. All right, so I'm going to divide over and get 4.184 times 100 times 2 divided by 15.6 divided by 73. I'm going to get 0.734. And then you want to put joules per gram degree Celsius. Okay. All right, the next thing you want to do is realize that if I have two things and I don't know the final temperature, that gets a little bit tricky. I am going to make an assumption here that both the coffee and the creamer are going to have a heat capacity very close to water. So I'm going to put in a heat capacity for coffee and milk at 4.184 on both sides. The milk's mass is 5.6. And the thing here that you want to do is you don't know what the final temperature is. It's certainly going to be hotter than the 25, so it's super important to put T minus 25. 4.184, 100 grams. And the other thing you want to do here is that the coffee is definitely going to cool down, so minus T. Now, you can cancel that. If you didn't, you'd want to multiply that through. Thing you want to do is make sure you do the distributive properties. So I'm going to finish this up real quick here, but making sure you multiply these two and then gather your T's. And I'll do this real quick because I only have a few seconds left here. And so 98, not 9.8. Okay, so I would add 100 T to both sides to get 105.6 T, and I would add this to both sides. Okay, And I'd get a number here. I would divide both sides by 105.6 T and get your final temperature there.